Well, what a big day we've got here today. We're going to look at some exponential modeling problems that are focused exclusively on some financial investments, and just kind of a congratulatory moment to pat you on the back and say, nice job, just getting sticking with it until you got to this point, because we've been planting seeds and laying the groundwork, so to speak, to kind of get us to this moment where we could actually do something useful that may actually pertain to the real world outside of your normal academic building. So let's take a look. Obviously, with our investments, we like to make an investment and watch the balance grow, really by just letting the interest rate do its thing, allowing it enough time to grow. And if nothing else, we're going to see that the power of compounding interest is an amazing thing. All right. So the power of compounding interest. So as far as what have we learned in the past that we're going to use today? So the basic general form of an exponential function, is y equals a times b raised to the x. Okay. Now, in the case that we're decaying, if your base is less than 1, we would replace b with a 1 minus r, and now the equation generally looks like this. However, if your base is greater than 1, that implies that we're growing. We would replace your b with a 1 plus r, and now all of a sudden your equation looks like this. So very, very similar, just a difference of whether we're adding the r or subtracting the r. And one really interesting thing that we've noticed up to this point is how the coefficient of your exponent really dictates the frequency of your rate. That sounds like a mouthful. So we're going to work through some examples and try to sort this out. So we're going to just talk through our interpretations here as we look at these equations. And if we were to assume that in this first one, t is measured in days, whoops, didn't mean to write on that. So if t is measured in days, now look at this, look at your exponent. The coefficient of t is simply a 1, and that is what we call the best case scenario. So in this particular case, we would say that we're increasing at a rate of 2% each year. Okay, done deal. We won't need to worry about anything other than that. Or like in this second example, you'll notice now t is measured in hours, and the coefficient of my exponent is a 1. That's a 1t. So we'll say we are decreasing or decaying at a rate of 7% each hour. Okay, all we did is we took our 0.93, we subtracted it from 1, got 0.07, moved the decimal twice, and that's how I got my 7%. All right, now things are going to gradually get a little more interesting. So let's say we'll go back to t's measured in years. If I saw t divided by 2, what I'm saying is that the coefficient of t is a 1/2. So what we'll say is we're increasing at a rate of 16% every, how often? Every 2 years. Okay. Now what I want to do is I want to kind of convert that to an annual rate. So we're going to manipulate this bear. We'll go 1.16 raised to the 1/2. We'll pump that into our calculator. And now what I could say is we're increasing at a rate of 7.7% each year. So that part's nothing terribly new. Now, but watch this. If I just make a subtle change here, so let's say t is still measured in years, but look at the coefficient now. The coefficient's a 2. So that's a slightly different interpretation. And let me show you what it is and see if we can make some sense of it. We'd say we're increasing at a rate of 16% every 6 months. Now, whoa. Where did you get 6 months? Well, in this case, the frequency being a 2, we would say it's happening twice per year. Twice per year. And when you say something's happening twice per year, an equivalent form of that would be to say every 6 months. Okay. Now, of course, we could rewrite this and get an annual rate, and we'll go 1.16 squared, close the parenthesis, raised to the t. And from there, we could say we're increasing at a rate of 34.56% each year. All right. So the key is, though, so when we saw the 2t, the coefficient of the exponent was a 2, that meant it was happening twice per year. And we converted that to every 6 months. All right. Let's see if we can tackle a few more. So in this next one, we'll say we're increasing 34% at a rate of 34%, okay, every 12 years. So that's over a pretty long span. Compare that to the next one, though. Look at how your coefficient's going from a 1/12 to just a 12. So now we're increasing at a rate of 34% each month. You're like, whoa, where did you get each month? Well, what we're doing is we're saying the frequency here is 12 times per year. And if you do something 12 times per year, you're effectively doing it once a month or each month. Okay. All right, let's try this next one. So the coefficient of t is a 1/4, and t is described as being in days. So we're increasing at a rate of 8% every 4 days. Now, how does my interpretation change when the coefficient changes from a 1/4 to a 4? So ultimately, what I'm thinking is this rate of 8% is happening 4 times per day. Okay, so we can make that note. It's happening 4 times per day. So what's another way to say that? Let's think about that for a second. We're increasing at a rate of 8% every 6 hours. So when something happens 4 times in a day, that's equivalent to saying it happens every 6 hours. So there's some new interpretations that we're gradually going to get a little more comfortable with. I want you to imagine this scenario. You invested $4,000 into a savings account that pays 4% compounded monthly. So we're compounding it monthly. How much money would you have in that account to the nearest dollar 10 years from now, assuming that no money was either added or withdrawn from that account? You just basically made a one-time deposit, you forgot about it for 10 years, and then magically 10 years from now, how much is that account worth? I think you're going to be pleasantly surprised. Well, what we're doing here today is this is an example of what we call periodic compounding interest. AKA, maybe it got compounded annually or semi-annually or quarterly or monthly, et cetera, et cetera. Now, we'll also study something called continuous compounding interest, and we'll talk about that in our next video. So today we're just focused on the periodic compounding interest. Now, the formula we use for this, and this is probably the worst news of the day, is this formula does need to be memorized. Okay, so but I think as we practice, it's kind of like the quadratic formula. Once you practice it enough, like you start to remember it without even like really trying to memorize it per se. And believe it or not, it's not that much different than the growth formula we've been using. So up until today, when we would say something's growing exponentially, we would have used this function right here. And you'll notice it's very, very similar. We've just changed, the letters a little bit, and we're basically, and we have this new letter for n. So we're going to try to define each of these letters. So for us, the capital letter is the amount of money after T years. Okay. Now this capital letter P is what we'll say is the principal. If I could spell, that would help. AKA the original amount of money. And the leading coefficient has always represented the initial amount or the original amount. So I hope that's nothing drastically new for us. Okay, R is your interest rate. And in the parentheses here, I want to make a comment that we want to always, we'll say, written as a decimal. So we always want to move the decimal place twice on those. Now, N is the number of times the interest is compounded per year. Per year. Well, my handwriting's not the sharpest today. So the number of times the interest is compounded, or another word for compounded, if you want to think of it this way, is paid. The number of times the interest is paid out from the bank to your account each year. And of course, T will be the number of years since the original deposit or investment. Now, if we go back to the frequency here, the letter N, a couple of common ones we mentioned earlier. When something happens annually, we would say N equals 1. If something happens semi-annually or twice per year, N would be 2. If something happens quarterly, N would be 4. And if something happens monthly, we'll say N is 12. So those are like the really common ones that we'll see throughout. All right, so let's see if we can make some sense out of this. So let's see if we can finish this first example. I'm sorry, I'm scrolling all over the place. So we invested $4,000, okay? So let's say the amount of money I have in my account is equal to $4,000. And we're going to do 1 plus R, written as a decimal, divided by 12 raised to the 12t. So compare that so that the formula, just to make sure we're all seeing the formula here, would normally look like this. And I replaced the P with a 4,000, because that's my original investment or deposit. I replaced the R with a 0.04, and I replaced N with a 12, because that's the number of times that the interest is going to be compounded on a yearly basis. So if they wanted to know, in this case, how much money would you have 10 years from now? Let's say A of 10 equals 4,000. We'll go 1 plus 0.04 divided by 12 raised to the 12 times 10. So we're substituting a 10 for T. Let's see. So on my calculator, I got $5,963, and we'll just round that to the nearest dollar. And that's for doing nothing. So you received a free $1,963 from the bank just by investing that $4,000 and letting them use it for whatever they would like to use it for. Okay, so the power of compounding interest is a powerful thing. Here's another scenario to consider. You deposit $1,000 into an account that pays 6.2% interest compounded semi-annually. All right, let's highlight a few things here. This $1,000 is going to be your principal, so that's my P. This percentage tells me that R equals 0.062, and when something's compounded or paid out semi-annually, we would say N equals 2. It happens twice per year. So let's say the amount of money in my account as a function of time would be 1,000 and in parentheses 1 plus 0.062 divided by 2 raised to the 2t power. Cool. What would your balance be 5 years from now? So let's just evaluate this function, f5. Once we show our substitution here, we'll just grab our calculators. So it's going to be 2 times 5. We'll grab those calculators here. So I got, if we go nearest dollar, we'll go $1,357. Notice we haven't gotten rich per se, but we have earned $357 in interest for just letting it sit there for 5 years and not doing anything to it. So, and initially those first 5 years, you're not going to see a huge bang for your buck. But if you could let it sit there for 20, 25, or 30 years, that's when you'd see the greatest impact. So you just got to give it some time. Now, the next thing is we want to know how long would it take before your balance reaches 1,800. Now, that's the amount of money that you've accrued over the course of time. So I'm going to substitute that 1,800 for the A of t. Let me highlight that here. So I'm going to substitute that 1,800 right here. So we're setting the function equal to 1,800. And here's where things get real. So we're going 1 plus 0.062 divided by 2 to the 2t. So we're going to try to solve for t. First thing I'm going to do is I'm going to divide both sides by 1,000. We're going to earn our money here. And that's going to give us about 1.8 equals. Now I may, let's see if this comes out nice. I may just type this portion in and convert it to one numeral. That came out to be 1.031 raised to the 2t. All right, cool. So, and again, the trigger for me is where the variable is. Because of where that variable is, that's going to cause me to take the log of both sides. So let's say the log of 1.8 equals the log of 1.031 raised to the 2t. Next, our exponent can transform into the coefficient. So it's 2t times the log of 1.031. We'll divide both sides by the log of 1.031. And then we'll divide both sides by 2 eventually. So let's say, oh gosh, I'm going to take my time. Hopefully, if you're feeling good and you're ahead of me, that's awesome. So once I divide everything by 2, we'll have something like this. And we'll just plug this into our calculator and we'll round it to the nearest year. So I got 9.6, so I'm going to round that to the nearest year. So it's going to take you approximately 10 years for your $1,000 investment to grow to $1,800. Not bad, not bad. Okay, let's dream a little bit bigger here. So we're going to have some fun with some bigger numbers. Unfortunately, our interest rate isn't as glamorous as it was earlier, but we'll see what happens here. So let's say we're going to try to write a function. This is your initial investment, so there's P. We'll use this as our R. We just need to slide the decimal, so it's going to be 0.0495. Compounded quarterly means N will be 4. Let's see if we can put it all together here. So the amount of money in my account as a function of time is going to be my $250,000. Maybe we won the lottery or something like that. 0.495 divided by 4, because it's quarterly, raised to the 4t power. Good. So there's my function. Find the balance after 10 years. So we'll substitute a 10. 0.495 divided by 4 raised to the 4 times 10. Okay, if we go nearest dollar, I got 408,880.5. So I'll go 881 if I go nearest dollar. So not bad. Your $250,000 grew to $408,881 in a 10-year period without you making any more deposits into that. You just let it be. Just let it sit and grow. Now, how many years would it take before your balance doubles? In fact, let's get a little crazier. I'm going to edit this one on the fly. Let's cross off doubles. Let's say triples. How long before my investment triples, huh? So we started with 250,000. Tripling that would be 750,000, and I'm going to substitute that for A of t. In other words, we want to set the function equal to 750,000. And okay, typing in this portion into my calculator, I got 1.012375. Be careful, we don't want to round anything off at that point. We need to carry all those decimals. So the first thing we're going to do is we're going to divide both sides by 250,000. Giving us just a nice clean 3, which makes sense because we're tripling. Then we'll take the log of both sides. And we know that that exponent is going to transform into the coefficient. So it's 4t times the log of 1.012375. And then we'll just divide both sides by the log and divide both sides by the 4. So we'll have the log of 3 first divided by the log of 1.012375. And then we'll divide that entire thing by 4. So I got about 22.33. So we'll say approximately 22 years for that investment to triple. So again, that's the power of investing early. We want to start investing as early as we can. As soon as we graduate from college, start making some investments, and just by the time you retire, you're going to have fun with your retirement. So we'll get into class tomorrow. We'll practice these, and I think we're going to be very, very good at these.